Having seen that, now we will apply this signal to the code. So see here, output equal to, I'm plotting the time response of fit, noisy input, sample time. I'm passing this noisy input as the input signal, and I have to pass the sample time, and I have to pass the parameter fit. Fit is the parameter which is going to be the giving the data proper polynomial fit for my transfer function. After plotting, I am viewing the, I am just running this command, so it will generate the output object. And now when you run this command, you will find the time response and the frequency response of the graph. This is the input. Again, there is some problem with title. Okay, so I'll comment all the title. Wherever I have title, I'm going to comment just to avoid any hash. You get three outputs. This is the input signal. This is the noisy input signal, which we have seen already, right? Now they are plotting, and this is the time response. This is the filter output. You know, filters work in frequency domain. So from the time response, I cannot make out anything. The time response is good only if I analyze I have a transfer function to see whether what I wrote is correct or not, right? So when I have a filter and if I see the time response, it is not going to give me any meaning. Time response is looking like a varying sine wave. I can only make it out from that. Only if I take FFT and see, I can clearly understand whether my filter is working or not. See here, I'm taking FFT for the noisy input and I'm plotting the output. I'm plotting the transfer function of the filter and I'm plotting the output spectrum. Here also, I think we have this title. So I'll comment this title so that we don't have an error while compiling. I'm running this code. Yes, you can see when I run the code, a black thing is running each line. Else, you can see here, a black thing is running. This running, it is compiling each line. Okay. Now see, this is the filter transfer function. It's a bandpass filter. See, rather than this third diagram, this is very meaningful for us because when I work with frequency, time domain representation will not carry any meaning, or I cannot make out anything from the time domain. So see the frequency response, it is flat between 2.4 and 2.5. Any frequency between 2.4 and 2.5 will be allowed. Anything above this range will be completely rejected. You know that the noise signal what we have sent is 2.35, correct? So it has to be rejected, and the signal 2.45 will be passed. See the next diagram. The input plus noise. See, the input is two signal, one at 2.35, one at 2.45. You can see two green. And over one green, you have the red, which is the output. So output 2.45 gigahertz is allowed by the signal, and this 2.35 is completely blocked by the signal. Even though you see a small peak, see this one is close to 1, this one is close to 0.1. So the difference is very, very less. So this will be completely, you can assume it to be ignored. This is a very, very simple example of constructing a bandpass filter using MATLAB. This is going to work at high frequency, 2.45 gigahertz, or I can say the ISM band of frequencies. All your Wi-Fi, Bluetooth, WLAN, all these applications use 2.45 gigahertz.